from Université de Genève, and he will talk about large toric charts on coadjoint orbits.
So thanks a lot. Thank you very much for an invitation to this exciting meeting. In fact, the story that I want to tell you today, it's more like a program than one talk. So for this reason, kind of one has to choose a little bit what one does, the results or the methods. And even though the methods are maybe somewhat more interesting, we'll still maybe start with the results, at least to give you something. And then towards the end, maybe I say a little bit about those interesting methods and interesting phenomena. So let me introduce the two definitions. So what are those toric charts? So the idea is as follows. Suppose we start with a real torus of some dimension, let's say m. And let's consider its cotangent bundle. So that's a product of Rm and Tm. So let's call coordinates lambdas on Rm and phi's on Tm. And then, of course, this cotangent bundle is symplectic. With symplectic form, well, I never know what's the correct sign. So let's say maybe we choose this sign, but yeah, no guarantees about the signs. And now let's take U an open subset of Rm. So then, of course, U times Tm is still symplectic with the same symplectic form, and this will be our toric chart. So this is essentially like Darboux charts, but half of the variables there are angles, and the other half we call actions usually. So this is some kind of pre-baked action angle variables. Now let me just briefly recall conjoint orbits. So we're going to consider compact connected Lie groups. So then let me denote by this beautiful G the Lie algebra. Let's say inside capital G will be a maximal torus. So then we are interested in the dual to the Lie algebra. And by abuse of notations, let's say that we think of the dual to the torus inside G star. So this is not entirely functorial, but we can arrange it like that. And we choose here some element. Well, again, sorry for using the same letter. Usually we call it lambda. So then the coadjoint orbit, O lambda, is, of course, just the orbit of the coadjoint action. And, well, by the standard wisdom, it is symplectic. And let me, just for completeness, and anyways, I have a little bit of space here on the blackboard. So let me write this symplectic form on two fundamental vector fields. So the famous formula is the pairing of lambda with a Lie bracket of psi and eta. And the question is how we can build as large as possible toric charts within coadjoint orbits. So here, in some sense, the difficulty is the coadjoint orbits. We can imagine them as some kind of roundish objects. Now, those toric charts, well, I don't know how one can imagine them, right? These are those U's. So these are some kind of cylindrical objects, right? You have this torus times the piece of Rm, and you want to symplectically fit such a chart inside a coadjoint orbit. So, so the question is, so we would like this U times T of some appropriate dimension. Yeah, let me still leave it to be M, and then we'll discuss what it is. So we want it to map in the symplectic way inside the coadjoint orbit. And if possible, say, what does it mean large? Well, maybe we can ask the symplectic volumes to be the same. So, so here the volume is with respect to this symplectic form, this Darboux form, and here with respect to the KKS symplectic form that I wrote on the other blackboard. So this is a classical question, and it has, in various cases, it has many interesting answers. So, so one classical fact about it, so these are the Gelfand-Zeitlin integrable systems due to Gilman and Sternberg. So this applies for the case of G UN or SON. And maybe later on I'll show a little bit of a glimpse of how those, at least some very simple example of Gelfand-Zeitlin integrable system. Now there is the whole technology called toric degenerations, which is doing this for lambda, a rational element of T star. And so this is one of the important works is by Megumi and by Kaveh. And today I'll be talking about another technology which at the moment applies to lambda being regular elements of the Weil chamber. So these are coadjoint orbits of maximal dimension, but probably it applies to other cases, but it needs more work. So this is a result of many papers and a collaboration with many people. I will. So this is Arkady Berenstein, Benjamin Hoffman, Jeremy Lane, and Yang-Peng Li. And actually, so this project, it started long ago. We had some unpublished thoughts with Eckhart and Chris Woodward, and then published thoughts with my former grad student Irina Davidenkova. So, so I'll be speaking about this story. And maybe, as I said, maybe let me first formulate some results, and then we'll discuss a little bit how those results can be obtained. For that, let me introduce a little bit of notation. So let me denote by capital N. So the sum of the dimension of G and the rank of G over 2, and by small n, so the difference of dimension and rank over 2, and actually this is half of the dimension of our regular coadjoint orbits. And then this is the number of action and angle variables that we want to have. So then an important thing will be a certain cone, convex polyhedral cone, inside R capital N. So this cone, first, I won't be saying much about it, and then I will introduce some implicit description, and then towards the end, if I have enough time, I will introduce explicit description of it. But it's important that it comes with a map to the Weil chamber. And this map, by analogy with representation theory, it is suggestively called highest weight. So there is a linear map from that cone to the positive Weil chamber. And so under this, the preimages of elements of the positive Weil, of the interior of the positive Weil chamber, of the regular elements of the positive Weil chamber. So these are convex polytopes. Of dimension, of full dimension, so dimension n. So this, this map has rank equal to the rank of the group. So the preimage is a hyperplane. It intersects the cone inside Rn and cuts a polytope in there. And so we have the following. We'll have the following equality. So 2 pi to the power n, which of course comes eventually from the volume of the torus on the future chart, multiplied by the Lebesgue volume of the polytope, exactly equals to the volume of the coadjoint orbit. So there will be a cone with this property. So now I am ready to state a couple of results. So one result will be about coadjoint orbits, and one result will be more general. So here is the theorem. And in fact, from this theorem, you will see that in my promises already, I was cheating a little bit. But how is it? In a talk, one is supposed to cheat. But usually one starts cheating towards the end. I started already pretty much in the beginning, so you will see. So a theorem. So for all lambda in the regular part of the Weil chamber, and for all delta bigger than 0, there is a toric chart which symplectically maps into the coadjoint orbit. And here, well, suspiciously, right, there is this delta. So what is it? So we've got a polytope. So let me draw it on a plane as if it were a triangle. So this is the polytope delta lambda. So we cannot quite do as promised, meaning that we cannot quite match the volumes. However, if I step by an arbitrary delta, whatever, in some distance from the walls, so I make a slightly smaller polytope. So then we know how to make a symplectic embedding like that. So, and delta can be anything, so arbitrarily small. So arbitrarily small positive delta. So we'll come back to this story. We'll see that it would be desirable actually to close that gap. But at the moment, we don't quite know how to do it. Not necessarily, but yeah, let's come back. If we have time, we'll discuss it a little bit. So that would be one of the open questions. So we do want to, in principle, we want to make delta equal 0. And in particular, I think it is the case in those two methods. So there it is, actually there is no delta. However, even with this delta, there is an interesting corollary of this theorem. So I don't know that much about it, but I think it's an interesting consequence. So there is a notion of the Gromov-Witz of a symplectic space, and this is a supremum of the radius of a symplectic ball inside your space. In our case, that's an orbit. So computing those symplectic Witzes of coadjoint orbits is an interesting question, and it has a kind of funny status. It seems, at least as far as I understood, it is more or less solved, but not entirely. Let me tell you what this means. So on the one hand, the answer for a coadjoint orbit is supposed to be the minimum for positive roots of the following products of the weight with those core roots, such that, and you consider non-zero ones. So that's supposed to be the answer. And what is known about it is the following. So there are many results. Maybe I state the latest ones. First of all, so this is an upper bound for the Witz, and this is obtained using the Gromov-Witten theory. Sorry? Sorry? Root?
The root alpha is integral?
You mean the positive root of G? Oh, I think, how is it? You mean for the group G? Yes. No, I don't think so. I think it doesn't, right, the coadjoint orbits, how is it? They do not depend on the, so you can think that everything is, the G is simply connected. It doesn't matter. So I think I wanted to give a reference. Now let me see. Am I able to give the reference? Hopefully, yes. Now it would be a little bit bad if I spell the name in the wrong way. I hope it's correct. And then in the other direction, it's established for lambda rational. And that's the work by, also recent work by Fang, Littleman, and Pabinek. But it looks like this lower bound, one knows it for lambda rational, but still one doesn't know it for all lambdas. So it looks like what this construction gives it for all lambda in the interior of the Weil chamber. So still remains something on the walls that we don't know. So let me give you one more result, and then one very, very simple example. So in fact, our technology can do more than coadjoint orbits. And I give an example of a result. It won't be the most general one. So let's suppose that we have a Hamiltonian G space, which is multiplicity free. So in particular, all reduced spaces are points. And let's assume the following. So let me denote by xg. So I take the image of M. I divide it by the coadjoint action. So this will be in the Weil chamber now. And let me intersect it with the interior of the Weil chamber. And let me assume that this is non-empty. So you have some regular points in the image. And let's assume that the dimension of xg is equal to the rank of g. So you have some kind of in the Weil chamber. So you have some points with non-trivial neighborhoods contained in xg. So then one can build not a dense but almost dense integrable system using this method, namely for any delta positive. So there will be the following thing. We take a pre-image, remember, right, there is this highest weight map. We take a pre-image from the Weil chamber to C of this xg. And again, we step away from the boundaries by this delta. We multiply it by the torus of dimension capital N. And we embed it into M symplectically. Let's assume, to simplify things, that M is compact. In principle, one can also do non-compact cases, but then one needs to take pieces of M. But in case it's compact, so we can take this pre-baked integrable system, and we can simply map it into our multiplicity-free space. And this is a symplectic embedding. So ready with actions and angles. So the actions are taken values in this mysterious column C. The angles are just the angles. So as I say, now we're gonna learn more about C. The N here is this. So according to my assumptions are such that 2n is the dimension of M.
What's the relation of that diagram, that inclusion, with the original
with the original?
So if you compose that map with the moment map, what happens?
Yeah, there would be a relation. For instance, I didn't introduce it, but in fact, C. Let me put a secret link. So in fact, secretly, we don't speak about it, right? C is also equipped with another map to T star. Let's call it the weight. Again, according to representations theory. And here we also have a map to T star, just a projection. So for instance, they will agree. And one can say more. And of course, this highest weight map will agree with the map to the Weyl chamber, which is given by the quotient by the coadjoint action. So I think, yeah, these two things, but one can in principle say more. Right. So let me give you a very, very elementary example. You know, even though the real interest of the story is doing arbitrary types of G, but still I will first give you an example of SU2 and then eventually give you an example of SU3. That's because, you know, those other types, they are really scary. In principle, one can do it, but so an example. So G is equal to SU2. And we look at the coadjoint orbit. And coadjoint orbits are two spheres. So we take a two-sphere of radius r. So instead of lambda, I have here the parameter r. And so what will be the cone? So the cone, let me do the following. So the cone will be the set of points of R2 with coordinates. Let me call them, no, maybe let me exchange Z and R such that the absolute value of Z is smaller than R. And this is the simplest instance of the Gelfand-Zeitlin cone. So let me draw the cone. So this will be the Z-axis, and this will be the R-axis. So that's the cone. So that's the cone C. Now, the highest weight projection of ZR will be equal to R. So that's just projection on the vertical axis. And the polytopes delta R, so suppose I've chosen some R, so this is the polytope delta R, which is of course now just a segment which extends along Z from minus R to R, right? So our chart is S1 times this segment, minus R to R. And now I want to map it. So here I have, say, a point phi Z. And I want to map it to the two-sphere. So it maps, well, you can imagine what it is. R squared minus Z squared square root cos phi. R squared minus Z squared square root sine phi, and Z. So that would be the standard Gelfand-Zeitlin chart, a toric chart in a two-sphere. So that's how roughly we expect those things to look like, at least in the simple cases. Okay. So now let me develop the story and let me give you some ideas of how we prove it. So that's a long story, so I will try to concentrate it into some steps. And in those steps, to be honest, I only tell you the nice part. Whenever it comes to some dirty work, I just basically don't mention it. Of course, you can always ask me, but, you know. And we're only going to speak about coadjoint orbits. We're not going to speak about multiplicity-free spaces. So, so the first major step, which is known for a long time, is as follows. So let me recall that if I denote like this, the killing form on the complexification of G, so on the complex, say, semi-simple Lie algebra. Let's assume that it's all semi-simple. So then the imaginary part of this form, it establishes a perfect pairing between G and the sum of the, say, nilpotent and what is called A. So A is the imaginary unit times the Lie algebra of the torus. Right? So this is actually a Lie algebra of GC. And so this is a perfect pairing. OK. So then, so let's denote by capital G star the corresponding group inside GC, so the product of A and N. And so the standard wisdom from Poisson Lie groups says that there is a unique Poisson structure on G star, such that if you apply this Poisson structure to the following gadget, I write, say, right invariant Maurer-Cartan form on that group. I write it in some kind of matrix notation, right? So that's a Maurer-Cartan form, as if they were matrices. So pairing with some element psi in G. So here I'm using that perfect pairing. So this will be equal to the fundamental vector field. And this fundamental vector field I define using the following. This is also isomorphic to GC mod G. So G acts on the left, and that's the corresponding vector field. So that's also a formula that Liu used to define her moment maps. So that's a Liu formula. And this uniquely defines the Poisson bracket. We'll return to the discussion of that Poisson bracket a little bit. So this is the first thing. So there are Poisson Lie groups, and in particular, there are those Poisson spaces that I described here. So for each group G, you can define it in this way. Of course, this is somewhat implicit, so we'll have to talk a bit more about those formulas. So now step 2. So this is also some classical result due to Ginzburg and Feinstein. And this result says that there are global Poisson isomorphisms between small g star with the k-chaos Poisson bracket and the capital G star with this Poisson bracket that I implicitly described over there. So this is a deep result which has many different proofs. Maybe we will also come back in some minutes to the discussion. But important to know now that there are many such Poisson isomorphisms. Indeed, you can compose with any Poisson isomorphism of G star on the left or any Poisson isomorphism of capital G star on the right, you get a new one, right? So that will we'll return to the discussion shortly. And now let me just put some small remark, which goes under the name of scaling. So indeed, we know that the Poisson bracket here is linear, right? So if you take small g star with the Poisson bracket pi k ks, you can simply multiply all your coordinates by some positive real number. And this will establish for you a Poisson isomorphism with a multiple of pi k ks. So that's obvious, right? You just scale coordinates, you get a scale, you get a multiple of pi k ks. Now, if we continue with gamma, we obtain G star with a multiple of this Poisson bracket, right? Naturally. So let's denote this composition. Let's denote this composition by gamma s. So in principle, you can always map your linear Poisson bracket with its symplectic leaves, being coadjoint orbits, to this Poisson bracket with its symplectic leaves, whatever they are, with a multiple of the Poisson structure, with S arbitrary. And what we want to do, we want to take S arbitrarily large. So that will be the technology. Right? So you can choose any S. In particular, you can choose S arbitrarily large. And the idea, which doesn't quite work, but almost would be just to send S to infinity. So the idea is that S maybe should go to infinity. Of course, for S to go to infinity, as I put it now, it doesn't make much sense. Of course, if you take a Poisson bracket, right, the Poisson bracket will simply go to infinity. And what does it mean? However, here we bring in another technology. And so these are special coordinate systems. And this technology comes from the theory of cluster algebras. So I'll give you an example of G equal to SU3. But in fact, you will see that this example basically generalizes to the arbitrary case relatively easily. So an element of G star in this case, so remember, it lives in the product of A and N. This is something like an upper triangular matrix. So these strictly upper triangular elements are complex numbers, and on the diagonal you have positive reals. So that's how they look like. And we're going to introduce the following coordinate system. First of all, let's factorize it into the diagonal and into the product of the so-called Jacobi matrices. So all the matrix elements that I don't write, they're zeros. So, and this is a coordinate system which covers almost everything. So it's not a global one, so you can take it as an exercise. There are upper triangular matrices which don't factorize in this form, but it's a dense chart. Now let's do the following. Let's say that AIs, I said they're positive reals, so let me let me introduce the following parameterization, which now depends on S. And for xi, they are complex numbers. So let me introduce this parameterization. The absolute value of xi is, again, has this exponential change of variables with s in it, and for the angles, we just leave the angles. So, that's a particular parameterization, particular coordinate system, and maybe I should say that in general, such parameterizations, they're in one-to-one correspondence with reduced words for the longest element of the while group. So you take this word, and using this word, you can write such a parameterization. In particular here, the word is S1, S2, S1. And you can also, for instance, by moving x1 here, x2 there, and x3 to the lower corner, you would get S2, S1, S2, and so on. So this exists in arbitrary type. Now there is quite an interesting theorem. Hopefully, I don't know whether you find it surprising. I find it very surprising. So up to now, it all looks a little bit strange, right? But on the other hand, you see, we have the Poisson bracket on G star. That's the Poisson bracket that we want to study when specified to a particular coadjoint orbit. We now replaced it. This was more or less understandable. We replaced it by some incomprehensible bracket on capital G star, which in addition to everything, when s goes to infinity, it probably blows up. Now we introduced even kind of less comprehensible coordinate system, which also contains s. Now, the theorem says that actually after all these manipulations, so the Poisson bracket S pi star has a good limit when s goes to infinity. So, so let me write it in the following way. So in fact, it tends to a constant Poisson bracket in terms of our coordinates. And this constant Poisson bracket is something like this. So there are some constants. And the brackets between alphas and phis, and maybe some other constants for the brackets between xi's and phis. And there are no other terms. So actually, up to some linear change of variables, it is a toric chart. Maybe one more thing. Yeah, two more things. But actually, what I said, it's not quite true. It's true on some cone times a torus inside Rn times Tm. So you see our coordinates, we have capital N of them, alphas and xi's. So they belong a priori to our capital N. And then we have a somewhat smaller number of angles. So, and in fact, so this limit exists, and it looks so nicely only on the product of a cone and a torus. And outside, we'll say a bit more about it, but it probably just doesn't make sense. It diverges when s goes to infinity. Nothing good happens outside that region. So if I add one more thing, so a fact, right here we have a constant Poisson bracket. So this constant Poisson bracket pairs capital N action variables with small n angle variables. So a priori, it's degenerate because capital N is bigger than small n. So it has symplectic leaves, right? So it turns out that there is this highest weight map. to the Weyl chamber such that the preimages of points are leaves of this Poisson bracket that I will denote pi infinity. Right? So they are symplectic leaves. So then here I said there is a cone, but actually this description tells you what this cone more or less uniquely if you add the following condition. So the volume of L lambda equal to the volume of O lambda. You see, actually, this cone, you can take it smaller, right? Suppose there is a cone for which this is true. But take a smaller cone. OK, it's also fine. But then what's the biggest possible cone that I can take such that nothing bad happens? It turns out that the biggest possible cone is such that the volumes of the leaves will be exactly the volumes of coadjoint orbits. And then you cannot get bigger. So that's the biggest there is. So there is a unique cone. There is a unique maximal cone with this property. So this is an implicit description of the cone. I think I will still have some minutes to tell you an explicit description. But maybe now let me try to draw a picture of what's going on. So suppose this is our space Rn, and here is this cone C, and that's the torus Tn. So that's what things are going on. Now, suppose that this is this pre-image. Let's call it delta lambda. The symplectic leaf L lambda is a product delta lambda times Tn. So, and its volume is equal to the volume of the coadjoint orbit. But now let's take S big but finite. In those coordinates, in those like really strange coordinates, we can draw symplectic leaves of this Poisson structure. They are isomorphic to coadjoint orbits, right? Because the Poisson structures are isomorphic. So imagine that S is large, but not too large yet. So you will have this roundish symplectic leaf. Now, S becomes bigger. All right. S becomes even bigger. Whatever. You see what happens. The symplectic leaf, when it meets the cone, it will get closer and closer, actually exponentially fast. It will fall on this delta lambda. But actually, it will have huge parts outside. However, on the symplectic leaf, you have a symplectic form, right? And this symplectic form, it wants to flow to the intersection with the cone. So for instance, when we're here, so this part of the leaf is very, very thick with symplectic volume. And here there is almost nothing on this remaining part. So this phenomenon we call volume concentration. You see, that's kind of surprising and interesting. Maybe not that surprising. We'll see it now from some formulas. But roughly speaking, the Poisson bracket doesn't tend to anything here. It explodes, which means that the symplectic form goes to 0, right? Because that's the inverse. So the symplectic form here, it dies out. The symplectic form wants to live here, where the Poisson bracket is constant. So that's a kind of interesting and surprising picture. We don't have much control of what's going on here, but we have pretty good control of what happens here. And actually, that's the only thing which matters. Maybe I say one more word on how the proof is completed. And then, so this was the step, this will be the step 4. And then I'll tell you a little bit more about the construction of the cone. So essentially, you see, with S very large, you get this portion of the coadjoint orbit of the symplectic leaf, which is very close to this tropical leaf. Right? So basically, all the volume, maybe with some very small things, it's here. Now, here you can then identify them with some standard symplectic techniques or Poisson techniques around the Moser trick, Moser flow, and then identify them. Essentially that's how it works. So that's why, in particular, that's why we don't quite know those small pieces, because the Moser flow near here, it would not be good. So you have to stop somewhere a little bit outside. Maybe one question. So we have this coordinate system which depends on S. We can think of it as a map from capital G star to Rn times the torus. And what we are doing, we are composing it with the Ginzburg-Weinstein map. I mean, this would have been ideal if this guy actually converged to something, right? If it converged, it's relatively easy to see. It would have converged to a Poisson map, and this would give you an integrable system on a coadjoint orbit more or less directly, similar to Gelfand-Zeitlin type. There would be, still it would be dense, but kind of you wouldn't have this problem with the small things. And here it depends on how you choose gamma S. So actually, for SUN, we know how to do it. So we use gamma that we built some years ago with Eckhart, and then we proved that actually there is a limit. But SUN is not a super interesting case because there you already know the Gelfand-Zeitlin system. So from that perspective, it would be interesting to do it for other types. And yeah, the problem is that even though all what I said is true, it's not guaranteed that this thing converges, right? It may spin very fast when S goes to infinity. Things may happen with it. So that would be the ideal scenario. Now let me finish with some brief description of what is C. And that's a very interesting piece of material because it involves something which is called the Bernstein-Kazhdan potential. So we're using this gadget, but we don't really know what its true relation to Poisson geometry. So the Bernstein-Kazhdan potential is a function on G star. And I'll describe it in the case of SU3. So remember, we have those upper triangular matrices. And so this will be some ratio, some sum of ratios of minus. So I will draw those minus for you. And then state the result. So the minus are like this. So here you simply take this matrix element, here this matrix element, here this matrix element. And here you take this corner minor, and here the minor like this, and here the minor like that. So this is a sum of ratios of minus. So one fact is denominators are always monomials in terms of those coordinates a and x. I invite you to do the exercise. That's actually surprising and interesting. So they turn out to be monomials. So this actually means the following, that this gadget, if we express it in terms of those coordinates, it will be a sum of some coefficients, let me call them W, which maybe depend on the angles. And here, this will be some linear forms of alpha and psi, right? So this will be a sum of exponentials of linear forms with some coefficients which are trigonometric functions of phi's. Now, the cone C is described as follows. We require all these linear forms to be negative, right? So these are linear inequalities which described for you the wall, so maybe they're superfluous somewhere. So we described for you the facets, the faces of the cone. And actually, if you go back to the Poisson brackets, so the Poisson brackets, for instance, psi I phi j, they look as follows. So there is this constant, ij, right? This constant which corresponds to s equal to infinity. And it turns out that here there would be a sum of other coefficients, I don't know, w tilde, ij, b of phi, and here there will be some other linear functions. So that's how they roughly look like. So they have an exponential behavior. Sometimes this exponent is equal to 0, but usually it's not. So Irina Davidenkova, one of my former grad students, she wrote those expressions explicitly for SU3. Well, I mean, in 3 pages you can fit it if you plan your LaTeX well. In general, it's kind of a horror story. So here there are zillions of those terms. Now, one of the theorems, or maybe the main technical theorem that we are proving is as follows. If those functions, those linear forms in the potential, they are smaller than 0, then all those things are also smaller than 0. So then on the cone, all this garbage dies. So it goes to 0 on C. Or sometimes we say that this Poisson bracket is dominated by the potential. So there is one function which tells us what is its behavior for S large. Now, why it is like that, it remains a mystery. So we know how to prove it, fine. But I mean, what's the relation? What's the importance of this function? This function, or some version of it, should be important for our Poisson geometry. And we don't know why it works, but it does work. So let me end my talk with this small miracle. I think it's also like in 8 seconds which is left, I won't be able to say much more.